Hi guys, my name is Jelle Hofman. I'm working as an air quality researcher for IMEC, and within this 3-minute time window, I would like to present our innovative IoT approach for air quality mapping in cities. Let me first start by sharing a poster. There you go. Monitoring air quality in cities is challenging, as ideally high resolution in both space and time are required to accurately assess population exposure. We, as IMEC, together with universities of Ghent and Brussels, developed an IoT approach consisting of, first of all, a sensor testbed. In this case, a combination of fixed and mobile air quality sensors mounted on postal vans in Antwerp, Belgium. Secondly, we developed a cloud calibration algorithm improving the data quality of these sensors based on knowledge from existing regulatory monitoring networks. And thirdly, different machine learning approaches were tested, in this case two models, one deep learning model based on variational graph autoencoders and a random forest model to infer those calibrated air quality data in both space and time. This work focused on the validation of this approach by presenting data quality improvements by cloud calibration on the one hand, and temporal validation results of the applied machine learning models on the other hand. To test the calibration performance, we co-located sensors next to a reference monitoring station, calibrated the sensor readings based on other somewhat distant reference stations, and subsequently evaluated the calibration by comparing the calibrated readings with the co-located reference measurements. From the graph and the poster, you can see the effect of the cloud calibration as the calibrated sensor readings, denoted in blue, clearly approach the reference measurements, shown in green. Certainly, may compare them to the original data, so the raw sensor data, shown in red. The associated performance metrics of the raw and the calibrated readings are presented above in the table and clearly show improvements of the accuracy, the linearity, and the correlation due to the cloud calibration. We repeated this exercise for 5 different locations in Antwerp, and they all yielded similar results. To evaluate the model performance, we predicted NO2 concentrations during March 2020 at 3 different locations in Antwerp, so at location 801, 802, and 805, and compared the predicted values with the observed sensor readings. From the table, where the 2 models are presented, so the variational graph autoencoder model in the upper panel and the random forest model in the lower panel, we can see that both models perform fairly well, with mean absolute errors of around 10 micrograms per cubic meter and correlations around 0.7. So, based on these results, combining mobile sensors and data inference models has potential and opens up a range of new applications for researchers, policymakers, and environmental agencies, including real-time hotspot detection, traffic flow optimization, source attribution, and ultimately more accurate exposure assessments. So this was it. Thanks for watching. Feel free to contact me to discuss any further, or if you have questions, ask them now.